All right, let's try another one here. This would be from chapter 10, number, what is this, 30. And so number 30 here is asking for the kinetic energy of a rotating cam. And before we even get into this problem here, let me point out something that I hope you got out of the reading, and that is that the total moment of inertia of something can be calculated by adding up the sum of the pieces. Let's say it's made out of n pieces. Then you would go the moment of inertia of the first one, and then the second one, and then the third one, and so forth, and so on. So that's how you would get the excuse me, the total moment of inertia of an object. And that's what this problem is going to boil down to, because it does ask for the kinetic energy. And so the kinetic energy of rotation is this, 1/2 I omega squared. And they say, what is the kinetic energy of this cam when it's rotating at a speed omega? So it really boils down to really this. What is the moment of inertia? And so that's why I started here with this statement, that that's really what we need to remember here. And also, kind of an interesting trick here, if I had something that looked like this, this is not quite what this cam looks like, but if it looks sort of like, and let me switch to a pencil here so I can do some erasing, because I try to make this look as best as I can, and in 3 dimensions I probably won't do a real good job here, but let's say that I have a cylinder here. And then, in addition, there is a second cylinder of, say, half the radius. Let's see if I can make this look good. But this second cylinder is then mounted onto the first. And it all spins around the axis of the smaller one. And I'm hoping that picture looks somewhat decent, because what I'm trying to point out here is, if we were to call this bigger one the moment of inertia of number 1, and then the smaller one the moment of inertia of number 2, I would then say that the total moment of inertia is 1 plus 2. And, of course, that's not quite what we have. What we have looks sort of like this, where we have our big cylinder. Which again I'll call number 1. So this is moment of inertia of number 1. But then if you could imagine that we take a second cylinder like we did here, but that cylinder is actually a negative mass, And we kind of merge the two together, and so this right here, cylinder number 2 with negative mass 2. And then it's this one here. When you combine the two together, you actually get then a hole. And that's what this problem is. This problem is trying to get the moment of inertia of a big cylinder with a hole cut into it, an off-centered hole, and it's rotating around that axis. And so this is the rotational axis, so that as it spins around this axis, this big cylinder called the cam, so here's the cam part of it, would go up and down. And so if you had this hooked to something and some kind of lever system here, as this thing rotates, this is going to go up and down, and so whatever's on this end is going to go up and down, and we can open a valve and then close a valve, and it spins around here. So this cam part really is a big cylinder with a hole cut out of it. And all of this is trying to set up the problem that I know the problem asks for the kinetic energy, but that really boils down to getting the moment of inertia. And then that really boils down to realizing you're going to add up a bunch of pieces. And then the real trick to this problem is right here, in case you missed it, is we are going to think of this cam as made out of two objects. One is a big cylinder, and the other one is a small cylinder with a negative mass. Because when you take a negative mass and you combine it then with the positive mass from that first cylinder, the net effect is no mass, and that's a hole. And so that's how we get a hole here. And so what I want to do then is to really focus on this picture right here and this equation right here and say, what is the moment of inertia of this cam, by saying it's two cylinders. And so I'll put that here and say, okay, let's look at moment of inertia of number 1. All right, so number 1 is this big one, and it is a cylinder, but also notice it's a cylinder that is rotating not around the center of the cylinder. This would be the center of the big cylinder. It's rotating around the center of the small cylinder right here. That's why the big one then, as it goes around, kind of makes this wobble, goes whoa, and up and down as it kind of spins here. And that's the whole idea here of this wobble. I don't know if I have anything close at hand that would kind of illustrate it here. Maybe the best I have is this big paperweight here. But if I use my pen here as the marker, as it spins around there, you can kind of see that this, I'll call this top edge here, goes up and down. And so if there was some kind of rod hooked to it, the rod would go up and then down. And as this thing spins, it would go down, and then it would go back up, and something like that. And so, again, that's referred to as a cam. So I'll say it again. I want to think of this problem right here as made out of a big cylinder and a small cylinder. And the small cylinder is actually negative mass. So again, that when we put the big cylinder together with the negative mass of the small cylinder, we end up with a hole. All right, so let's look at number 1. And so number 1, then, being a cylinder, but also rotating off of its center, I need to apply the parallel axis theorem to it. So the parallel axis theorem, of course, says take the moment of inertia around its center. And so I'll go back over to the chart there, and the chart says that the moment of inertia of a cylinder around its center is 1/2 times the mass of the cylinder, so let's call that m1, and then times the radius squared. And so looking at the picture in the book, the cam, and there's the book right here, the cam has a radius of r. Now the hole is going to have a radius of r over 2. So this is the diameter. So we'll come back to the small one in a second, but that's the big one here. So that's around its center. And then the part that it's off of center, and so coming here, we are then moving a distance of, let's see if this is r, we're going to go r over 2. So it would be the mass of number 1, and we're moving a distance of r over 2 squared. And so the moment of inertia here would be a 1/2 from this first term, and then this would be plus a 1/4, and they would each be the mass of cylinder number 1 and radius squared. All right, so keep that in the back of your mind. That would be the moment of inertia of the big cylinder, which is going to be the first part of the cam. And the second part of the cam is we're going to add to it a negative mass. Let me ignore the negative mass for just a moment, but let's just find out the moment of inertia of number 2. And so the moment of inertia of number 2, again being a cylinder, and in this case, the cylinder actually is rotating the small cylinder around its center. So we don't need the parallel axis theorem. We just need to go to the table and look up the 1/2 mass number 2, and then its radius is the r over 2 that I pointed out a moment ago. And of course, maybe I should put absolute value there and say, okay, this is the moment of inertia if it was, a cylinder of mass number 2, because eventually I'm going to treat mass number 2 as a negative number here. But looking at that, this is a 4.5, make a 1/8, mass number 2. I'll just do absolute value, and r squared. So now I can come back to what I was saying. The total is the two of them together. And so the first one here, maybe I should have simplified it, but that's a 3/4 m1r squared. So I'll put that here. So 3/4 of m1r squared added to a 1/8 of mass number 2r squared. And maybe I'll fix this right now, because so far I haven't really treated it as a negative mass, but let me do that now. And so this is saying that I am taking a solid cylinder and then adding to it a smaller cylinder that's rotating around its center but has a negative mass, and so that's why the subtraction comes out there. Okay, well, now another little piece of this, and maybe I'll draw another cross-section here. But if you look at a circle that has a radius of capital R, and another one that has a radius of half of that, remembering that the area of a circle is pi r squared, the big one here then would have 4 times the area of that one. And so in terms of mass, M1 should have 4 times the mass of the smaller one. And again, maybe I should be careful with my sign there, but what I mean by that is the absolute value. So if this really was a cylinder, this cylinder would have 1/4 of the volume compared to the bigger one, and therefore would have 1/4 of the mass. And so I can use that here to say, okay, so this is my total moment of inertia, and so it's this 3/4 m1r squared. And then right here I would say minus 1/8, and in place of this m2, and I guess I don't like the way this looked really. This was really minus, yeah, I I apologize here that this probably would have worked better to say, you know, minus the absolute value of it. Okay. And so coming back to here, minus, this is the 1/8. And so M2 would actually be M1 over 4, if I do that right. Yeah, M1 over 4 times R squared. Okay, and so as I simplify this first term is 3/4, okay, minus, and this is a 1/32, I guess, 8, 16, 32, okay, and then I have M1 R squared. And then getting a common denominator of 32, I'd have to multiply that by 8, so this is 24 minus 1 is MR squared. And so this becomes 23 30 seconds, M1 R squared. All right, now, even then I'm not quite done because this is written in terms of mass of a big cylinder that is solid. You know, that was this whole idea. Mass number 1 is solid. And your author uses the symbol, I think it's M. Let's see, the mass capital M. Okay, so your author says that the cam itself is capital M. Now, I think you can agree that capital M is going to be smaller than M here by a little bit. In fact, we can again hopefully see the numbers here in this this 1 to 4 ratio, or in this case, it's going to be the 3 to 4, because 3/4 of M1 should be the mass of the cam. Because again, if you let this be the M be the mass of the cam, if a solid cylinder was you know, M1, then think of it into 4 parts. You're missing one of those parts. So M is 3/4 of M1. Or put another way, as we keep working on this, it's 23 over 32, and then M1 would be 4 over, let's see, 4 over 3, capital M R squared. And then this 4 would go into here 8 times. And so this would become a 23 over a 24 MR squared, where the capital M is the mass of the cam itself, the whole mass. And so that's not, you know, not the mass of the big cylinder solid. It's not the mass of the little cylinder or the negative of it, but it's the true mass of it, because the true mass of the cam is only 3/4 of what a solid cylinder would be. Okay, and then finally we can finish, which just brings us back to right here, and that is then the kinetic energy for a rotating object is 1/2 I omega squared. And of course, then here's the 1/2, and the I is the 23 over 24 mass of the cam R squared, and then omega squared. And then I guess we can put the 23, and then the 2 and the 24 make 48, and then M R squared, omega squared, and voila, we finally have it. Yay!